Today we're reading from How Linux Works, What Every Super User Should Know, the third edition by Brian Ward. And this is a pretty good book. I've read a lot of this, and it has taught me a lot about, how Linux actually works, since I tend to use Linux pretty much day to day. Not as my main operating system anymore, but obviously I used to, and for work and all that stuff, and especially with databases and DevOps and Kubernetes and all that stuff, programming, you're using Linux regardless whether you want to or not. So I think this is very important to know. And I'm making this video mostly because there was, a while ago, I think a couple years ago, there was this video on YouTube about Linux ASMR. It was just some guy narrating a book about the history of Linux and Multics and all that stuff, and that video was gone all of a sudden. So if anybody knows where I can find that video, that would be great. But today we're going to be reading from this book. We're going to read from chapter 6, How Userspace Starts. This is page 137, and I'm a little bit sick. My nose is a little, how do you say that, stuck, and my throat hurts a little bit, so we're going to try to do this right, and hopefully enjoy it. So hopefully it relaxes you a little bit, and that'd be great. So here we go. Chapter 6, How User Space Starts. The point where the kernel starts in it, its first user space process is significant, not just because the memory and CPU are finally ready for normal system operation, but because that's where you can see how the rest of the system builds up as a whole. Prior to this point, the kernel follows a well-controlled path of execution, defined by a relatively small number of software developers. User space is far more modular and customizable, and is also quite easy to see what goes on in the user space startup and operation. If you're feeling a little adventurous, you can use this to an advantage because understanding and changing the user space startup requires no low-level programming. User space starts roughly in this order. Number 1, init. Number 2, essential low-level services such as udevd and syslogd. Number 3, network configuration. Number 4, mid and high-level services, cron, printing, and so on. Number 5, login prompts, GUIs, and high-level applications such as web servers. Introduction to Init. Init is a user space program like any other program on the Linux system, and you'll find it in /bin/sbin, along with many of the other system binaries. Its main purpose is to start and stop the essential service processes on the system. On all current releases of major Linux distributions, the standard implementation of Init is Systemctl. This chapter focuses on how Systemctl works and how to interact with it. I had a very big discussion a couple years back with a friend who's very into Linux on Systemctl and OpenRC. I was using Gen 2 with OpenRC, I think, and usually I'm a pretty big Systemctl guy because it's just what I'm used to. And he was a big fan of OpenRC, and we got into a really big fight about that. just Linux things, right? But anyway, there are two other varieties of init that you may encounter on older systems. System V or 5 is a traditional sequenced init. SysV is usually pronounced Sys5, okay, with its origins in Unix System 5, found on Red Hat Enterprise Linux, RHEL, prior to version 7.0 and Debian 8. Upstart is the init on Ubuntu distributions prior to version 15.04. Other versions of init exist, especially on embedded platforms. For example, Android has its own init, and a version called Runit, is popular on lightweight systems. The BSDs also have their own version of init, but you're unlikely to see them on a contemporary Linux machine. Some distributions have modified the System 5 init configuration to resemble the BSD style. Different implementations of init have been developed to address several shortcomings in the System 5 init. To understand the problems, consider the inner workings of a traditional init. It's basically a series of scripts that Init runs in sequence, one at a time. Each script usually starts one service or configures an individual piece of the system. In most cases, it's relatively easy to resolve dependencies, plus there's a lot of flexibility to accommodate unusual startup requirements by modifying scripts. However, this scheme suffers from significant limitations. These can be grouped into performance problems and system management hassles. The most important of these are as follows. Performance suffers because two parts of the boot sequence cannot normally run at once. Managing a system can be difficult. Startup scripts are expected to start service daemons. To find the PID of a service daemon, you need to use PS, some other mechanism specific to the service, or semi-standardized system of recording the PID, such as /var/run myservice.pid. Startup scripts tend to include a lot of standard boilerplate code, sometimes making it difficult to read and understand what they do. There is little notion of on-demand services and configuration. Most services start at boot time. System configuration is largely set at that time as well. At one time, the traditional Init daemon was able to handle on-demand network services, but it has largely fallen out of use. Contemporary Init systems have dealt with these problems by changing how services start, how they are supervised, and how the dependencies are configured. You'll soon see how this works in Systemctl, but first, you should make sure that you're running it. Identifying your Init. Determining your system's version of Init usually isn't difficult. Viewing the Init1 manual page normally tells you right away, but if you're not sure, check your system as follows. If your system has /usr/lib/systemd and etc/systemd directories, you have systemd. If you have an etc/init directory that contains several .conf, I don't know how to say it, files, you're probably running Upstart, unless you're running Debian 7 or older, in which case you probably have System 5 in it. We won't cover Upstart in this book because it has been widely supplanted by Systemd. If neither of the above is true, but you have an etc/init tab file, you're probably running System 5. Go to section 6.5. I didn't realize how in-depth this was going to be. Okay. The Systemd. The Systemd init is one of the newest init implementations on Linux. In addition to handling the regular boot process, Systemd aims to incorporate the functionality of a number of standard Unix services, such as cron and initd. It's very difficult to pronounce all these, suffixed with d services, because it doesn't make sense to read. It takes some inspiration from Apple's LaunchD. Where Systemd really stands out from its predecessors is its advanced service management capabilities. Unlike a traditional init, Systemd can track individual service daemons after they start and group together multiple processes associated with a service, giving you more power and insight into exactly what is running on the system. Systemd is goal-oriented. At the top level, you can think of defining a goal, called a unit, for some system task. A unit can contain instructions for common startup tasks, such as starting a daemon, and it also has dependencies, which are other units. When starting or activating a unit, Systemd attempts to activate its dependencies, and then moves on to the details of the unit. When starting services, Systemd does not follow a rigid sequence. Instead, it activates units whenever they are ready. After boot, Systemd can react to system events, such as the U events outlined in Chapter 3, by activating additional units. Let's start by looking at a top-level view of units, activation, and the initial boot process. Then you'll be ready to see the specifics of unit configuration and the many varieties of unit dependencies along the way, you'll get a grip on how to view and control a running system. Units and unit types. One way that Systemctl is more ambitious than previous versions of Init is that it doesn't just operate processes and services. It could also manage file system mounts, monitor network connections, and run timers, and more. Each capacity is called a unit type, and each specific function, such as a service, is called a unit. When you turn on a unit, you activate it. Each unit has its own configuration file. We'll explore these files in section 6.3.3. These are the most significant unit types that perform the boot time tasks on a typical Linux system. Service units control the service daemons found on a Unix system. Target units control other units, usually by grouping them. Socket units represent incoming network connection requests, locations. Mount units represent the attachment of file systems to the system. You can find a complete list of all unit types in the System 1 manual page. Of these, service and target units are the most common and the easiest to understand. Let's take a look at how they fit together when you boot a system. Booting and unit dependency graphs. When you boot a system, you're activating a default unit, normally a target unit called default.target that group together a number of service and mount units as dependencies. As a result, it's somewhat easy to get a partial picture of what's going to happen when you boot. You might expect the unit dependencies to form a tree, with one at the top branching into several units below for later stages of the boot process, but they actually form a graph. A unit that comes late in the boot process can depend on several previous units, making earlier branches of a dependency tree join back together. You can even create a dependency graph with the system-analyze command. The entire graph is quite large on a typical system, requiring significant compute power to render. And it's hard to read, but there are ways to filter units and zero in on individual points. Figure 6.1 shows a very small part of the dependency graph for the default.target unit found on a typical system. When you activate that unit, all of the units below it also activate. On most systems, default.target is a link to some other high-level target unit, such as one that represents a user interface startup. On the system shown in Figure 6.1, default.target groups the units necessary to start a GUI. I say GUI, a lot of people say GUI, but we all know it's a graphical user interface. And here we have a sort of a root node that says default.target, and that points to multi-user.target. That points to basic.target, and that points to sysinit.target, and then multi-user.target also points to cron.service and dbus.service. This figure is a greatly simplified view. On your own system, you won't find it feasible to sketch out dependencies just by looking at the unit configuration file at the top and working your way down. We'll take a closer look at how dependencies work in section 6.3.6. Systemctl configuration. The systemctl configuration files are spread among many directories across the system, so you might need to do a little hunting when you're looking for a particular file. There are two main directories for systemctl configuration. The system unit directory, global configuration, usually /lib/systemd/system, or /usr/lib/systemd/system. In the system configuration directory, local definitions, usually /etc/systemd/system. That's where I put my stuff in anyway. To prevent confusion, stick to this rule. Avoid making changes to the system unit directory because your distribution will maintain it for you. Make your local changes to the system configuration directory. This general rule applies system-wide. When given the choice between modifying something in USR and etc, always change etc. Okie dokie. When you check the current systemd configuration search paths including precedence with this command, systemctl-p unit path show. To see the system unit and configuration directories on your system, use the following commands. Package or pkg-config systemd variable equals systemd system unit dir. And also the same thing, but with systemd system conf dir. Unit files. The format for unit files is derived from the XDG desktop entry specification used for .desktop files, which are very similar to .ini files on Windows systems, with the section names in square brackets and variable and value assignment options in each section. As an example, consider the dbus-daemon service .service unit file for the desktop bus daemon. And then it's essentially written out there. That format reminds me of the like AWS config and AWS credential file. It's basically the same thing, I think. XDG desktop entry specification. That's good to know. I don't think I would ever use that, but well, I don't know. Depends. There are two sections, unit and service. The unit section gives some details about the unit and contains description and dependency information. In particular, this unit requires the dbus socket unit as a dependency. In a service such as this, you'll find the details about the service in the service section, including how to prepare, start, and reload the service. You'll find a complete listing in the systemd.service 5 and systemd.exec manual pages, as well as in the discussion of previous tracking of process tracking in section 6.3.5. Many other unit configuration files are similarly straightforward. For example, the service unit file sshd.service enables the remote secure shell logins by starting sshd. The unit files you find on your system may differ slightly. In this example, you saw that Fedora uses the dbus-daemon.service and Ubuntu uses dbus.service. There may be changes in the actual files as well, but they are often superficial. Variables. You'll often find variables inside unit files. Here's a section from a different unit file. This one for the secure shell that you'll learn about in chapter 10. And it's just a service file, really. Everything that starts with a $sign is a variable. Although these variables have the same syntax, their origins can be different. The $sign options and the $sign crypto policy options, which you can pass to SSHD upon unit activation, are defined in the file specified by the environment file setting. In this particular case, you can look at the /etc/sysconfig/sshd to determine if the variables are set, and if so, what their values are. In comparison, $main PID contains the ID of the tracked process of this service. Upon unit activation, systemd records and stores this PID so that you can use it to manipulate a service-specific process later on. The sshd.service unit file uses the $main PID to send a hang-up or hub signal to SSHD when you want to reload the configuration. This is a very common technique for dealing with reloads and restarting Unix daemons. I don't know if it's demons or daemons. I guess technically daemons, but I feel weird saying it. Okay. Specifiers. A specifier is a variable-like feature often found in unit files. Specifiers start with a %sign. For example, the %n specifier is the current unit name, and the %h specifier is the current host name. You can also use specifiers to create multiple copies of a unit from a single unit file. For example, one example is the set of Getty processes that control the login prompt on virtual consoles such as TTY1 and TTY2. To use this feature, add an @ symbol to the end of the unit name before the dot in the unit file name. For example, the Getty unit file name is Getty @service @.service in most distributions, allowing for the dynamic creation of units such as Getty TTY1 and Getty TTY2. Anything after the @ is called the instance. When you look at one of these unit files, you may also see a %I or capital R %lowercase I specifier. When activating a service from a unit file with instances, Systemd replaces the %I or %I specifier with the instance to create the new service name. Wow, that's quite a mouthful. Okay, Systemd operation. You'll interact with Systemd primarily through the Systemctl command, which allows you to activate and deactivate services, list status, reload the configuration, and much more. The most essential commands help you to obtain useful unit information. For example, to view a list of active service units on your system, issue a list-units command. This is the default command for Systemctl, so technically you don't need the list-units argument. The output format is typical of a Unix information listening command. For example, the header and the line for the --.mount root file system looks like this. By default, Systemctl list-units produces a list of outputs because a typical system has numerous active units, but it's still an abridged form because Systemctl truncates any really large unit names. To see the full names of the units, use the --full option, and to see all units, not just those that are active, use the --all option. A particularly useful Systemctl operation is getting the status of a specific unit. For example, here's a typical status command and some of its output. Systemctl status sshd.service. And it has a whole bunch of information. And it's active, so that's good. A number of log messages may also follow this output. If you're used to a traditional init system, you might be surprised by the amount of useful information available from this one command. You not only get the state of the unit, but also the process associated with the service. When the unit started, and a number of log messages is available, the output for other unit types include similar useful information. For example, the output from mount units include when the mount happened, the exact command line used for it, and its exit status. One interesting piece of the output is the control group, or C group name. In the preceding example, the control group is /system.slice/sshd.service, and the processes in the C group are shown below it. However, you may also see control groups named starting with systemd /system if the process of a unit, for example, a mount unit, have already terminated. You can view systemd related C groups without the rest of the unit status with the systemd cgls command. You'll learn more about how systemd uses C groups in section 6.3.5 and how C groups work in section 8.6. The status command also displays the only most recent diagnostic log message for the unit. You can view all of a unit's messages like this. Journal ctl --unit equals unit_name. You'll learn much more about journal ctl in chapter 7. And let's stop here for now. I feel like we've done quite a bit already. Really interesting. I mean, I knew most of this, but you guys may have not. I hope you enjoyed this video. watching, and I hope you'll be here to watch next time. So thank you.